Okay, so yeah, thanks for inviting me. This is sketching as a tool for numerical linear algebra. I'll cover several recent results in this direction. So I'll first discuss regression, mention exact regression algorithms, and then show how sketching can be used to speed up these algorithms. I'll show it for least squares regression, then least absolute deviation regression. Then I'll look at low rank approximation, show how sketching is useful in that context. And then I'll discuss some more recent results using sketching for an M estimation problem for regression, and also CUR decompositions. So let me just get started with regression and give you the basic idea how sketching is useful for obtaining faster algorithms. So in linear regression, so we're going to only focus on linear regression in this talk. And it's just a statistical method to study linear dependencies between variables in the presence of noise, right? So here's some example where we have Ohm's law being the voltage is equal to the resistance times the current. We have a bunch of voltage current pairs, which are points in the plane. And we're trying to find a linear function that best fits this data under some notion of fitness. And there are many different notions, and we'll discuss a number of them in the talk. So the standard setting is there's one measured variable B. In the previous example, this was the voltage. And we have a set of predictor variables, A1 through AD. In the previous example, D was equal to 1, and we just had the current being the predictor variable. And the assumption is that this measured variable and the predictor variables are linearly related up to some noise. So what that means is that B is equal to x naught plus A1 x1 plus dot 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 AD xd plus some epsilon. Where epsilon is assumed to be noise, and the xi are model parameters that we're trying to learn. So they're the coefficients of the hyperplane that causes these variables to be linearly related. By standard transformations, you can assume that this free coefficient x naught is equal to 0. And let me just cast this problem in. So now you're just trying to find a subspace, a hyperplane through the origin. Let me just cast the problem as in matrix form, so we can talk about it in this way. So you're given an n by d matrix A, as well as a vector B, and n is the number of observations, and d is the number of these predictor variables. And the regression problem is just to find a vector x star so that ax star and b are close. Okay, that's just the whole problem. And for this talk, we're going to consider the over-constrained case when n is much larger than d. So this is a common case that arises, and so there need not be a solution here, right? There need not be an x star so that ax star is equal to b. And there is a way here that we're going to assume that A has full column rank in this talk. You can actually using one of Lapshi's results, you can replace A with an A which has full column rank very quickly. But I won't get into that here. So let's just assume that. And what's going on with this slide? Okay, so so let me discuss a few notions of measuring closeness in regression. So probably the most common way of doing this is the least squares method. Right, you want to find an x star that minimizes the Euclidean distance between ax and b. Right, and just for notation, so ai star is the ith row of a. So this is just the ith observation bi minus the inner product of ai star and x. Yeah, so this has certain desirable statistical properties. So it's known to be a maximum likelihood estimator if your noise is Gaussian. And it actually has a closed form solution as well. So the solution to the least squares regression problem is given by x equals A transpose A inverse A transpose B. Right. So there's actually a closed form solution which comes from solving the normal equations to this problem, the so-called normal equations. Okay, so that's one form of regression. Another form is least absolute deviation or L1 regression. And here you're just trying to find an x star which minimizes the one norm between ax and b. Okay, that's typically the cost is less sensitive to outliers than least squares. The reason this is the case is because if one of your measurements bi is corrupt, is slightly bad, then you're trying a lot harder to fit it when you're squaring this difference in least squares than in least absolute deviation. And for L1 regression, you can also solve this in polynomial time just via linear programming. Okay, so we don't have a closed form solution, but we still have this, and you can create n auxiliary variables to deal with these absolute values. You can solve it in in poly ND time. Okay, right. So these time complexities for both of these problems are at least n times d squared, and we would like to solve these problems faster. Okay, are there any questions about? This is just the basic setup for regression.
Technically, that would be like a matrix multiplication exponent minus 1 rather than a square.
Yeah.
Right?
So for least squares, you can get n times d to the omega minus 1 if you use fast matrix multiplication.
And you're just talking about the dense case. You're thinking that the matrices are full.
Yeah. So this so far I'm just talking about the dense case. Yeah. Yeah.
There's another notion called total least squares, but which isn't so widely used. But that's another version of least squares, where instead of the vertical distance, it's sort of the perpendicular distance.
Oh, okay. Yeah, definitely. Yeah, there are so many notions of regression. I'm just covering a handful of them. Okay. Right. So those are some exact regression algorithms, and now let me introduce the technique of sketching as a way of speeding up least squares regression. So first we're going to relax the problem to an approximation problem. We'd like to output an x prime for which the Euclidean distance between ax prime and b is at most 1 plus epsilon times the optimal cost with high probability. And the way to use sketching is sort of a sketch and solve paradigm. So let me just state the idea here. So the idea is that you draw a matrix S from a random family of matrices, and I'll go over different families. Now S is a very wide fat matrix. It's a k by n matrix where k is small. So think of it as independent of n. And what you do is you compute S times A and S times B. And you just solve the regression problem in this much smaller space, where A has been replaced with S times A and B has been replaced with S times B. And you get some x prime, and the hope is that x prime is a 1 plus epsilon approximation. So depending on which families of matrices S that you choose, this can be shown to hold. Right, so this is sort of a black box reduction. You can solve this problem now exactly, say, by solving the normal equations. If k is small, so think of k as being polynomial in D, the small parameter, then solving this problem would take polynomial in D time. So really the only dependence on n in the time complexity is just computing S times A and S times B. Okay. Right, so how to choose the right sketching matrix S. So lots of random families of matrices work. The most natural that might come to mind is if S is just a matrix of IID normal random variables. So if the parameter k, the number of rows of S, is d over epsilon squared, you can show that actually this matrix S has this property that if you solve it in the sketch space, you get a 1 plus epsilon approximation. Of course, we didn't gain much by doing this because computing S times A might be, very expensive, right? S is a dense matrix of normal random variables. S times A could take nd squared time or even a little bit larger. And okay, so but at least we know there is some S that works. In a very nice paper of Thomas Sarlos, he showed that actually you can choose S from a much more structured random family of matrices. Namely, S can be what's called a Johnson-Lindenstrauss transform, or a fast Johnson-Lindenstrauss transform. And so what is that? So the goal is to try to choose an S so that you can compute this product S times A very quickly, and also that it has this this property that it works. So typically, S can be factored in the following form. It can be written as P times H times D. And what are these matrices? So D is a diagonal matrix. And the entries on the diagonal are plus or minus 1 with equal probability. And they're chosen independently. Okay? H is just the Hadamard matrix. So it's a fixed matrix. And P, all it does is it chooses a random small subset of rows of H times D. Okay, so it's just sampling a small set of rows. So note that actually S can be applied very quickly to a vector, right? If I want to apply it to one of the columns of A, I can apply a diagonal matrix in linear time. The Hadamard transform can be applied in n log n time to any n-dimensional vector. And I can also easily choose a small subset of coordinates of a vector in at most linear time. So basically S times A can now be computed, if I have D columns in A, and each column I'm applying S in n log n time, I can compute this matrix-matrix product in nd log n time, which is much faster than this nd squared time that we solve for IID normal random variables. Okay, so right, and why does this work? So I don't have a proof of this on in this talk. Intuitively, right, so what is P doing? P is sampling a small subset of coordinates, right, and trying to estimate the Euclidean norm of a vector. This doesn't work very well if the mass of the Euclidean mass of the vector is concentrated on a few coordinates. Right, sampling will just miss those coordinates. So the goal of H is to spread out the mass of these coordinates across all of the coordinates. Right, so this is like the uncertainty principle that I can't be both sparse in the time and frequency domain. Of course, H is deterministic, so I could apply this to H inverse times a sparse vector, and then it wouldn't work. So there's some additional randomness with this matrix D that makes it work. It's just some high-level intuition. Okay, yeah. So then it works for a fixed vector, and then you can get it to work for the entire subspace spanned by the columns of A by a net argument. But okay, so that's just some intuition. But let me say how you can do even faster. How you can exploit the sparsity of your input matrix A. So in a lot of applications, your input, although the previous time complexity was n times d log n, which is near optimal in the matrix dimensions, if you have a very sparse matrix A, you might want to do it even faster in time proportional to the number of non-zero entries of your input matrix. Okay, so it turns out you can do that, and we use a what's called a count sketch matrix which was a matrix inspired from the data stream literature. And so let me define what that is. So this random family of matrices, S, it's again, I have a k by n matrix S. Now k is a little bit larger. So recall in the Gaussian case, you get a d over epsilon squared by n matrix. Now k is, d squared over epsilon squared, still independent of n. But the nice thing about S is it's really sparse. Okay, so in fact, S just looks like the following matrix. So in each column, I independently choose the location of a single non-zero element, uniformly at random among the rows. And on that location, I put plus or minus 1 with equal probability. Okay, so that's the whole matrix, actually. I mean, it's very simple. So you can see that S you can multiply S and a matrix A in time proportional to the number of non-zero entries of that matrix A, right? Because for each non-zero entry, there's I look at the corresponding column and there's just a single non-zero value in that column. And surprisingly to me, that this actually works. That you get this guarantee of a 1 plus epsilon approximation if you solve the problem in the sketch space. Yeah.
Do you have to have d squared there? D would not be enough.
For this matrix, you have to have d squared. Yeah. You can increase the sparsity by a bit and still get order number of non-zero entries time and get a smaller value. Instead of d squared, you can get sort of d to the 1 plus arbitrarily small constant. And then there are other trade-offs too. Like you can get number of non-zero entries of A times polylog D with D times polylog. Yeah. And okay, so so we had a bit of a complicated proof that this actually works, and after that there were some very slick, simpler and sharper proofs by Meng, Mahoney, Nelson, Nguyen, and I'm going to present proof of Nguyen just on this slide that this matrix S actually works, gives this 1 plus epsilon approximation. Okay, so this slide is a bit technical, but it has the whole proof. So let's consider this adjoint matrix B, where we take the columns of A and we adjoin this vector, the column vector B, right? It's an n by d plus 1 matrix. And let U be an arbitrary orthonormal basis for the columns of B. Okay? And I claim that it suffices to show that for this matrix S, this count sketch matrix that we're choosing at random, that the Euclidean norm of SUX is 1 plus or minus epsilon for all unit vectors x. I claim this is all we need to show. Okay, so first, by linearity, if I show it for all unit x, then it preserves the norm of every u times x up to a relative 1 plus or minus epsilon factor. And now note that if I look at ax minus b for some fixed x, that's just some arbitrary vector in the column span of u, right? So if this holds for all, if I preserve all the norms of vectors in the column span of u, then this means for any ax minus b, the Euclidean norm of S times ax minus b is 1 plus or minus epsilon the Euclidean norm of ax minus b. Does that make sense? Okay, so what that means then is now I can do this sketch and solve thing, right? Because that means that if I solve for the optimal x in this sketch space, it has to be a 1 plus epsilon approximation to the original problem. Yeah?
Just check. So instead of putting the u inside there, you can just say it for all unit x in the span of the columns.
Yeah, exactly. Yeah. I'm just going to fix u for the rest of the proof. Any other questions? Okay. Right. So this is what we're going to try to show. Okay. So U has d plus 1 columns. So if S has dimension over epsilon squared rows, S times U is a d plus 1 squared over epsilon squared by d plus 1 matrix. And what I claim is that it suffices to show this following property, this operator norm property, and this will imply this this claim that it preserves the norm of all vectors in the column span. So what does this mean, that it preserves the norm of all vectors in the column span? So it means all the singular values of S times U are 1 plus or minus epsilon, right? Or in that range. Okay. Well, what does that mean? Well, if I look at U transpose S times U, like sort of the square of S times U, all the singular values of that are also between 1 plus or minus theta epsilon, right? Okay. Well, if I subtract the identity from that, then I'd like all the singular values there to be theta at most epsilon. Okay? So it suffices to show that this this operator norm is at most epsilon. Now I don't know how to do that, so instead I'm going to show the Frobenius norm is at most epsilon, which upper bounds the operator norm, right? Okay. So
even in the first operator norm, aren't you showing something stronger than just all the eigenvalues are between 1 plus minus epsilon? Like it's not for sure, but it's a stronger statement. Like okay, in the worst case it doesn't matter.
Okay. Yeah, I think it's actually okay. Right. So how are we going to show this? Okay. So Frobenius norm is really easy to work with, right? You can expand things. You can compute first and second moments, and that's how the proof works. So basically, what you can show for this matrix S, this sketching matrix, this count sketch matrix, is that it has the following matrix product result. If I take any fixed matrices C and D, I can approximate the product C times D as C times S transpose times S times D.
This is like in expectation, right? This is in the expected value.
So yeah, I didn't say this, the statement yet. So what you can show is that how good of an approximation is C S transpose S D to C times D? Well, it depends on the number of rows of S. Okay. I mean, so you can think of S as kind of like a hashing matrix, right? And intuitively, this increases the number of hash buckets. So what you can show is that for any fixed C and D, the difference in Frobenius norm squared is at most 1 over the number of rows of S times the Frobenius norm of C squared times the Frobenius norm of D squared in expectation. Okay. Now I'm not going to give the proof of this, but the proof of this is really just by expanding the sides and computing, the expectation, and I mean that's it, right? So this matrix S is very simple. I choose a single location, random location in each column, and put plus or minus 1 there. It's not hard to compute this expectation, given that I'm looking at Frobenius norm. So, okay. So, and then by a Markov bound, this is at most a constant factor larger with constant probability.
Great. Just a quick question, since I'm getting confused with transposes. What does SS transpose? What's the easy description for the distribution of S? S transpose S?
I mean, you'd like it to be an identity matrix, but it's not, because it has a small number of, S is a wide fat matrix, and S transpose is a tall thin matrix. So it's some.
I'm trying to figure out S transpose S is small or small.
No, it has the right dimension. So S transpose S is this square matrix, which is formed by the product of a tall, thin matrix S transpose and this wide, fat matrix S. Yeah.
So S transpose S is low rank.
Yeah, exactly.
So what you're saying is that you can have a low rank matrix approximating a full rank matrix accurately.
Yeah, accurately meaning that. Yeah.
Well, it's approximating it on a low rank subspace though.
I mean, it's approximating it in this sense. What do you mean? I mean, you're not approximating like the operator norm, right? You're not approximating this.
Right, but I mean, it's just sort of surprising that C times D could be full rank, and you're giving it a low rank approximation, which means that you can't do all the singular values.
Oh yeah, definitely. It's a Frobenius norm guarantee.
So that's just surprising.
Well,
Yeah.
so note it's the product of the two Frobenius norms. The Frobenius norm is naturally the dimension of C times its operating norm, sort of in an intuitive sense. So you basically have a D squared factor from the C Frobenius times D Frobenius.
That'll be the next step of the proof. Yeah, just hold it for a second. Yeah, it's okay. So yeah, so how do we apply this this matrix product result? Okay, so okay, so what do we we want to, as we said, this chain of reasoning, we want to bound this operator norm. So we can plug in C is equal to U transpose, and D is equal to U. Okay? So C times D is the identity matrix. And, U transpose S transpose SU is exactly what we want here. So it suffices to, bound this right-hand side by at most epsilon. And that's what you can do by, you want to choose a number of rows as small as possible so that this is at most epsilon. Well, what is the Frobenius norm squared of the matrix U? So it's an orthonormal matrix, so it's just D plus 1, its dimension. Yeah? So this is D plus 1, it's U transpose, this is D plus 1, this is U. So this thing is order D squared. And so as long as I choose my number of rows to be order D squared over epsilon squared, the D squares will cancel, and this will be at most epsilon squared. And I can take square roots. Yeah? Is there a question?
Oh,
Yeah.
Should S entries really be plus or minus 1, or should they somehow be scaled to compensate for the number of rows you've got in that?
S is actually plus minus 1.
So just imagine when you write that expression in there, sort of like the more rows, or maybe it's columns in S, I might be reversing them.
The fact is that S just has a single non-zero entry per column, so you don't get
any.
like if you had a Gaussian matrix, you'd have to scale each entry by 1 over the number of rows would be the new variance. But here, you just have a single non-zero entry per column, right? So I mean, if you think of just does that make sense? Like,
If you have k non-zero entries per column, you scale them by 1 over root k in general.
right. I mean, just think about applying S to a standard unit vector. This will just select one of the columns, and that should have unit norm. You don't want to, right? Like, so one of the columns just has a single non-zero entry. It's plus or minus 1. If I'm selecting that column, I don't want to scale it.
Okay.
No, I mean, something's not clear, please. Yeah.
It's that I need to draw the picture to see it. I think I got the picture in my notebook, but
Oh, of S, or
Yeah.
okay. So yeah, so S is very simple. So again, like S just has a single non-zero entry per column, chosen at a random location, and it's 1 or minus 1 with equal probability. So if I apply this to EI, I'm just selecting one of these columns. So the columns should have norm 1. And since they only have a single non-zero entry, that value shouldn't be normalized. It should be 1 or minus 1.
So for your result continuing on, how much will be dependent on you only choose one non-zero entry or the constant number of non-zero entry?
So this is very important in the sense that if you want this time complexity to be proportional to the number of non-zero entries of A, one versus a constant, is that the question? No, that's not. I mean, this just affects the leading. So it affects the constant in the leading order term, and it affects the poly D factor in the time in the.
No other constant between the two numbers.
Yeah, nothing immediate. That I see. Okay, so I don't know. Is the gist of this proof clear? Like, basically, we show this. The entire column space is preserved by showing this single operator norm bound, and we don't bound the operator norm directly. We instead look at the Frobenius norm, and for that we just do a second moment argument. Okay. So if this, so I'm just going to give a name for this. When I preserve the entire column space of a matrix B, so every norm is preserved up to 1 plus epsilon, I'm going to call that a subspace embedding. Okay. So we showed that, with d squared over epsilon squared rows, S is a subspace embedding for a d-dimensional space. Okay. All right. So that's actually the main. That concludes the part on least squares regression, right? So at this point, you've shown the correctness, and you just solved the problem in the sketch space. Okay. Let me now move on to L1 regression, and here sketching is used in a somewhat different way than for least squares regression. Okay. So for L1 regression, we again want to find an x prime for which the L1 distance between ax prime and b is at most 1 plus epsilon times the optimal distance with high probability. So, what would you naturally try to solve this problem? So natural attempt would be to draw a random matrix S from a k by n family of matrices for a small value of k, and try to do this sketch and solve technique, right? Of computing S times A, S times B, and outputting the solution in the sketch space, right? This would be a natural extension. It turns out that this doesn't really work. So the issue really is we don't have this random family of matrices. So why doesn't outputting the solution x prime in the sketch space work? Okay, so we don't know of a random family of matrices, k by n random family of matrices with a small value of k, for which if x prime is the solution in the sketch space, then we get a 1 plus epsilon approximation by plugging in x prime into the original problem. So this is just the issue. One thing we do know, though, is that we can find an S such that we get this weaker guarantee, that the one norm of ax prime minus b is at most d log d times the optimal cost. Okay, so at least it's independent of n, but it's not 1 plus epsilon. And we will use this fact to bootstrap to get a 1 plus epsilon approximation. But so most trivially you can get sort of a root n approximation just by solving the least squares problem and relating the 2 and the 1 norms. So this is giving something interesting. So what is S? So S is a matrix of IID Cauchy random variables. Okay, and I'll say what these are in the next slide. It's just some continuous random variables, and they have so the property that you get with this S is that it's a subspace embedding, for the column span of this of A together with B, but it has d log d distortion, and S has a small number of rows. It has d log d rows. Okay, so yeah, so what are Cauchy random variables? Okay, so they're not as nice as Gaussian random variables. They're very heavy-tailed. Here's their density function. If you try to compute their expectation, you get an integral that doesn't converge. They have infinite variance. So yeah, they're not very, it doesn't seem like they're very useful at all. I guess one question is, can we even generate them? And that you can. So the ratio of two independent normal random variables is distributed as a Cauchy random variable. Yeah, so at least you can populate this matrix S. So, what is the property that makes these things useful? So the property is that they're one stable. So what does that mean? So it means the following. If A and B are scalars, and C1 and C2 are independent Cauchy random variables, then if I look at A times C1 plus B times C2, this is equal in distribution to the absolute value of A plus the absolute value of B times another Cauchy, C, Cauchy random variable. Okay, so they sort of carry L1 information. In the same sense, if I add Gaussians, the variances add, so I'm carrying L2 information. This is the analog for L1. So if I'm multiplying a row of Cauchys times a vector, I get something distributed as the one norm of that vector times another Cauchy. Okay, so this is sort of the key property that is used.
Could you write the formula for this?
What's that?
Could you write the formula for the Cauchy distribution?
The PDF for this. So it's 1 over 1 plus x squared times the normalization.
So it would be like the slope of a random point on a circle, or? Oh wait, that sounds similar to the ratio of two.
Yeah, that sounds. Yeah.
I think that's what it is.
Yeah, I think that's right. Yeah. There's a nice survey by John Nolan on p-stable random variables, which I think has that way of looking at Cauchy random variables.
Does this property characterize Cauchy distributions?
Yeah.
Yeah, it does actually. Yeah. Yeah, I think that's right. Yeah. And actually, so p-stable random variables exist for any p between 0 and 2. We don't have closed form for the density functions for. Okay, I think we might have a closed form for p equals 0.5. I'm not sure, but for most of these p, we don't have a closed form for the density function.
So the C there is a function of A and B also, or not?
So this is so C is so C by itself is just an independent Cauchy random variable, which is a function of C1 and C2.
Oh, right, not of A and B.
So what is this property saying then? If C is a function of C1 and C2, then I don't understand what this property says. I thought you would want something like you take three independent Cauchy C1, C2, and C3, and then A times C1 plus B times C2 is equal to A plus B times C3.
In distribution.
So any distribution that satisfies this property
Is one? You're asking if this characterizes a Cauchy distribution?
No, I got confused by your comment about C depends upon C1 and C2.
So yeah, that's what my understanding. It says, like somehow if you take C2, like you take a true instantiation of a Cauchy variable like C1, C2, C, and then this happens in terms of distributions.
This happens in terms of distributions, yeah.
This is like a function of
Oh, yes. I'm sorry. Yeah. I mean, definitely C depends on C1 and C2. It's not a function of C1 and C2.
The fact that if you add two normals, you get another normal. But that
So if you add a normal distribution with variant or with standard deviation A to one with standard deviation B, you get one with standard deviation square root a squared plus b squared.
Okay.
Right. So here, instead of getting square root a squared plus b
It adds
squared,
L1 norm of the vector.
it adds L1 instead of L2. Right.
But C is independent.
Yeah, well, like they just think about this differently than we do. Yes. What they just say, what they just say is that if you take a times C1 plus b times C2.
I see. I'm sorry. Yeah.
Cauchy.
No, this is equality in distribution. Is that what's not clear? Yeah. Okay.
Like we talk about.
Yeah. No. I mean, sure. Yeah. Okay. When you prove it. Oh. Okay. Fine. Okay, so let me say how you use sketching to solve L1 regression. Okay, so basically, right, so again, we're going to create this adjoint matrix A and B. And now we're going to do something differently. So we're going to compute S times B, where S is this matrix of IID Cauchys. And what we're going to do is we're going to compute a QR factorization of this. Okay? So in the standard L2 sense, right? So Q has orthonormal columns, R is a change of basis matrix, Q times R is S times B. And the point here is that B times R inverse is going to be a wall conditioning of B in a certain sense. Note that S times B times R inverse has orthonormal columns. It's just equal to Q. But now I'm saying use this change of basis matrix R found in the sketch space in the original space and see what happens. Right? Does BR inverse have certain nice properties? Okay, so it has the following two properties, which might look a little bit weird, but I'll explain what they mean. So the first property is that if I look at B times R inverse, and I look at the entry-wise L1 norm of this matrix, it's not too large. Okay. Now, first of all, by itself, that's a useless statement, right? Because I can always scale all the entries of B down arbitrarily small. But there will be another condition. Okay, so let me first say why BR inverse has small entry-wise L1 norm. Okay, so one way of computing that is just to take the sum over all the columns of the one norm of BR inverse of that column. I mean, BR inverse times EI. Which we know, since S is a subspace embedding, is at most the sum over all the columns of the one norm of S times BR inverse EI. Okay, now S is a small matrix. It only has d log d rows. So I can relate the one norm to the two norm. And so this is at most the number of rows of S, d log d to the 0.5 times the sum of the two norms of the columns. Okay. But right, SBR inverse is just Q. This has orthonormal columns. So this is just equal to 1. So when I sum over d terms, I get some d times root d roughly. So I get a poly d as the sum of the L1 entry-wise L1 of this matrix. Okay, and as I said, that's not useful by itself, but you also have this additional property. And let me explain it. So for any vector x, its infinity norm is less than or equal to its 2 norm. SBR inverse has orthonormal columns. So I can just write this as SBR inverse x 2 norm. The 2 norm is less than the 1 norm. And now I use that S as a subspace embedding. So the 1 norm of SBR inverse x is at most d log d times the 1 norm of BR inverse x. Okay, so there are two properties here. The first property is that the entry-wise L1 norm is not too large. And the other property is if I apply BR inverse to any vector x, I can't shrink the one norm of x too much, right? Because the infinity norm is at most d log d times this one norm. If I just scaled all the entries to be very small, then this property would not hold. Yeah, go ahead. Yeah.
So the last inequality, is this something that holds with high probability for the Cauchy S, or is it?
Oh, yeah. So with constant probability, S is a subspace embedding it. It preserves all the vectors one norm up to a d log d factor. So this is a probabilistic statement. But
First one also?
this is also a probabilistic statement, yeah. So condition on the fact that S is a subspace embedding, preserving all vectors up to a d log d factor, and now perform this analysis. So these are two properties that you get out of this, and the nice thing about them is that they make, go ahead.
Is there a way to test whether S is a subspace embedding, and if not, to sample again?
For this application, is S a subspace embedding? I don't know. There should be some simple way to test this.
I don't think so,
No?
actually.
No?
Because I think for the problem of graphs, asking whether two graphs approximate each other in this sense is very similar to sparse cut. I thought about this a little bit.
Yeah, but we don't care about approximation, right? So sparse cut is easy if I allow an approximation factor.
Oh, if you only want to test are they a subspace embedding up to, if you're willing to say test with, is it either not an embedding at all or one up to like a d squared factor or something maybe.
That's a good question. So.
Because you would need to do something like this in order to turn this into a reliable algorithm to boost the probability of success. Right?
So like for the downstream application of regression, you could just run this independently some number of times, and then you get a regression vector, and you just compute the cost of all of these and take the best one. Yeah. So I didn't say why. So what does this even mean? The way we're going to try to solve L1 regression is we're going to try to sample a small number of rows of A and corresponding coordinate in B, reweight them, and just solve the regression problem on that sample, and use that as a solution for the original problem. And the sampling has to be done in a certain way. So it's going to be done. So let me just describe on the next slide. How do we do sampling? Okay, so this is just important sampling 101. We want to estimate the sum of yi's for non-negative yi's. And suppose we sample yi with probability pi. And we consider the following estimator t, which is the sum from I equals 1 to n of an indicator which says if yi was sampled times yi over pi. Okay. So then for any set of pi's that I choose, the expectation of this random variable, I get the sum of pi times yi over pi. I get what I want in expectation. The variance of t is upper bounded by the second moment, and the expectation of this thing squared is still pi. So I get pi times yi squared over pi squared. I can pull out sort of the maximum entry here, so I get a max I yi pi times what I want to estimate, just by canceling one of the pi's. So what you really want to show in important sampling is that this maximum is small. So you have small variance. We would like that this maximum to be bounded by epsilon squared times the quantity we're trying to estimate. So then we'll get a 1 plus epsilon approximation. This is a standard importance sampling framework, and for us, what we apply this framework to is yi is going to be the ith coordinate, the absolute value of the ith coordinate of ax minus b for a fixed x. Okay, so if I take this yi and I plug it into here, this is just the one norm of ax minus b, right? And I'm trying to use sampling to approximate the one norm of ax minus b for a fixed x. And I can't just uniformly sample the coordinates, right? So I instead do this importance sampling. And it turns out that if you set the probabilities, these PIs, to be proportional to the one norms of the rows of this well-conditioned matrix, BR inverse, times a poly D over epsilon factor, then this importance sampling actually works. That is that for a fixed vector, what is the expected number of samples also that I have? It's the sum of the PIs. And we said that the overall L1 norm, entry-wise L1 norm of BR inverse is poly D, is something small. So the overall expected number of samples is going to be poly D. This was an important point. And you can show that you can bound this maximum for importance sampling if you use these properties, which I won't say why. But you can use the well-conditioned, those two properties that I said about being well-conditioned to argue that this maximum is not too large. So that's for a fixed x, we preserve its one norm. Now, yeah.
Could you say why, what's the intuition that those PIs should add up to 1 since they're probabilities?
No, so these PIs, they don't add up to 1. So for each coordinate, I decide to include it with probability PI. The PIs actually add up to poly D. And that's, the PI is also, yeah, okay. So this shows that, if I do the sampling according to the row norms of this well-conditioned basis, importance sampling works, and I preserve the one norm of any fixed ax minus b in my subspace. Okay, with a slightly stronger argument, using Bernstein's inequality, you can show that you preserve the one norm with high probability. Okay, and now you put a net on the d-dimensional space, which is, say, the intersection of the subspace and the unit L1 ball. You have exponential and d vectors, but it's fine. Since you have very high concentration, you can union bound over all of them. This is the intuition. So that's the whole algorithm. You sample poly d over epsilon rows according to these one norms, and you solve the problem in this sketch space. And so formally, what does this mean? What does importance sampling mean? Well, I have this matrix T, which is diagonal, where I have a 0 on the diagonal if a row is not sampled. And I have 1 over the probability the row is sampled if I do sample it, right? So this is just implementing importance sampling as a matrix product. And what you can show is that via this argument that we just discussed, that you get this 1 plus epsilon subspace embedding property. So now you can to solve it in the sketch space using, say, linear programming. Okay, and so these are, okay, so let me just say that the most expensive operation in this is computing S times A. The other operations are done in the sketch space, finding this preconditioning. There is something here where you need to find the one norms of this matrix to sample, but you don't have to explicitly compute B times R inverse. You can just, it suffices just to have approximations to all the the row norms. So this can be done quickly. So really, if you look at it, the main bottleneck is computing S times A, where S is this dense matrix of IID Cauchy random variables. And you can speed this up in various ways, inspired by the ways for speeding up L2 regression. So one way is to choose a diagonal matrix of Cauchys and this count sketch matrix we talked about for L2. So Meng and Mahoney show that this also provides a subspace embedding. Instead of being d log d distortion, it's some poly d distortion. But the whole argument is goes through in a similar way. You can reduce the number of samples in the second stage, in this important sampling stage, if instead of choosing Cauchy random variables, you choose this. So it's a product of the count sketch matrix and a diagonal matrix, where now instead of these being Cauchys, they're reciprocals of exponential random variables. And this uses a nice stability property about exponential random variables that was inspired for us by work of Andoni, which is that if I take scalars yi and independent exponentials ei, then the maximum of yi over ei is equal in distribution to the one norm of y over an exponential. So it's max stable in this sense. Why is this useful? You can sort of interpret this matrix as a hashing matrix. And so when I multiply by a vector x, the maximum entry is going to be proportional to the one norm over an exponential. And this hashing matrix will sort of preserve the maximum value. The maximum in the hash bucket will be the maximum value. And so you get an embedding into L infinity, actually. But since it's low dimensional, it's an embedding into L1 as well. Okay, so this is, and actually, so for recent work on sampling-based algorithms with fewer samples, see Richard's talk later today. Okay, so let me just, I guess I don't have time to cover low-rank approximations. So let me just mention some results on concerning regression. So what we saw for regression is least absolute deviation regression and least squares regression. But there's a whole, you can imagine an arbitrary cost function on the coordinates. So you can suppose you define the function m from the reals to the non-negative reals. Then you can just look at the cost function of a vector as being m applied to each coordinate and summing these up. So these are called m estimators. And so least squares in L1 regression are special cases. Another interesting case that's studied in practice is called the Huber penalty function, where Huber is a mixture of L2 squared and L1. So near the origin, this function looks like L2 squared. But as I move away from the origin, it looks like L1. And there's a parameter you can choose so that when you flip from L2 to L1. This one nice thing about the Huber function is that it enjoys the smoothness properties of L2. So close to the origin, I have this smoothness property, and it also enjoys the robustness properties of L1. So it behaves like L1 for outliers. And in recent work with Ken, we show that for a class of m estimators which have at least linear and at most quadratic growth, you can get a constant factor approximation in roughly number of non-zero entries of your input matrix time. Okay, so I didn't get a chance to cover low-rank approximation. So I have a recent monograph on a lot of this stuff, which includes what I discussed and other problems concerning low-rank approximation that I didn't get into. And Yeah, so let me just conclude. That's all. Yeah.
Is there a way to do L2 to do sketching for L2 regression in a way that also guarantees that the residual is close to orthogonal to the column space of A? Because otherwise you don't get any guarantee on X. You get a guarantee on the residual, but not on the model.
Yeah. So basically, if your matrix A is reasonably well conditioned, you can get a bound which depends on the condition number of that matrix. So basically, how close X is to the optimal X star. Is that your question? Like,
yes.
Yeah.
It also depends. I think that also depends on how far B is from the column space of A, not just on the well.
Oh yeah. You'll have a multiplicative norm of B as well, I think. So this is in Sarlos's paper actually. So you can get. Let's see. So. I think it might be a dependence of like 1 over the condition number. I mean, so you can bound the difference in Euclidean distance between x and x prime as so I'm not entirely. I don't remember the bound exactly, but it's in Sarlos's paper actually. So, yeah, sorry, yeah.
Were there lower bounds on the size of these sketches? So in the L2 case, is d squared over epsilon squared necessary?
Yeah, for if you want only one.
Yeah, so there's this trade-off that I mentioned that if you have a single non-zero entry per column, you need at least d squared rows. But you can, if you have polylog d entries per column, you can get d polylog d rows. This is a result of Nelson and Nguyen.
And they also wrote a paper on lower bounds that includes the lower bounds in all of these cases as well.
Yeah, so there are also lower bounds. So actually, like for this matrix, it's not hard to see if you apply it to the identity matrix. You need at least d squared rows because you'll have a collision with constant probability of 2 of the columns, and they'll cancel, and the rank will be reduced from d to something smaller. So the hard instance is actually identity matrix for that sketching matrix.
There's also an interesting feature, which is that unless you have at least 1 over epsilon non-zeros per column, you can't squeeze below d squared at all. You need to jump. You basically don't get any benefit until you jump from 1 to about 1 over epsilon non-zeros per column. But then you can go down to arbitrary powers of d between 1 and 2.